Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about homogeneous equilibrium expressions, and I would like to talk about what happens if you know the concentrations and you're asked to calculate the value of the equilibrium constant. Now, this is the second video in a series of two. I did have a video that talked purely about how do you write an equilibrium expression, right? Because before you can do the calculation, you have to be able to write the equilibrium expression. So if you're not 100% sure on that, I do have the link to the video down in the description, so you can take a look at that. Might be a good idea to pause here and go back and check it out. But if you're feeling confident with your equilibrium expressions, we'll move on to doing some calculations. Now what I've got here is just a general equilibrium. Reactants turning into products, and I have the equilibrium expression, right? So if we do an actual example, let's say that we have some H2 gases reacting with some O2 gases in equilibrium with some H2O gases. To balance it, I would need a 2 here and a 2 here. Okay, so this is my equilibrium. It's the same as this, but I've included actual chemicals, right? So instead of chemical A and chemical B, I have hydrogen gas and oxygen gas. The lowercase numbers refer to the balancing, right? The numbers used to balance. So for these here, lowercase a, lowercase b would be like the 2 and the 1. So if I take a look at this here, in order to do my equilibrium expression, I am really talking about products divided by reactants, right? We take our products, put them in the top. We take our reactants, put them in the bottom. The square brackets refer to concentration, and the numbers that are used to balance become powers. So if you have A of A, little a of big A is the chemical, little a was the number used to balance it. So if we do something similar over here, we say that our equilibrium constant is equal to products, and there is only one product, H2O. We put it in square brackets to show concentration, and because it was balanced with a 2, that means the power is 2. In the denominator, we put in our reactants. So the first reactant is an H2. To balance it, there was a 2 in front, so I am going to square it. The second reactant is an oxygen gas, square brackets to show concentration. There was a 1 in front to use to balance it, so I'll put a 1 here. And although the reactants were added into chemical reaction, they are multiplied in the expression. So this entire thing is an equilibrium expression. Okay, so the whole thing is your equilibrium expression. The KEQ, that's your equilibrium constant. This is what we'd like to be able to calculate. Now, depending on what your worksheet looks like or who's teaching you your course, I've referred to them as KEQs, as my equilibrium constant. In some courses, they just call it K. And because this thing is all based on concentrations, sometimes we call it K with a subscript C, refers to concentration. Okay, so that's the quick overview. Again, if you are having some trouble with the equilibrium expression, you should pop back to the first video. Okay, so let's say we do a calculation or two. So it says, calculate the value of the equilibrium constant. So I would like to know what KEQ is equal to for each of the following equilibria. So I'm going to give you a bunch of equilibriums, and then I'm going to give you a bunch of concentrations. Now, the first step in any equilibrium problem is write your equilibrium expression. K equals products over reactants. That's your first step no matter what. So if I take a look at this, KEQ equals, first product is an H2O, square brackets to show that it's a concentration. Because to balance it, there's a 2 in front of it, my expression has a power of 2, right? So if you have 2 waters, the 2 was used to balance it. In my equilibrium expression, that becomes a power of 2. Now, if you have a second product, we'll write that one down as well. So that's chlorine. Square brackets to tell me that it's a concentration. Again, there's a 2 in front of it that was used to balance, so this becomes power of 2. And if you have more than one reactant or more than one product, there is a multiplication sign in between them, right? In the equation, they were added, but in the expression, they're multiplied. If I look down at my denominator, I have HCl as my first reactant. Square brackets give me concentration. Now, in order to balance it, this had a 4. So this is going to be power of 4 times the second reactant is an O2. Square brackets give me concentration. There was one of them, so it'll be power of 1. This is my equilibrium expression. First step in any calculation is find your equilibrium expression. Oh, and we are chemists, right? So writing out the word equilibrium takes too long, and so we do have an abbreviation. EQ/LBM is equilibrium. Because in the world of chemistry, we do a lot of work with equilibriums, and so we do use the abbreviation quite a bit. Now, the other thing that I should maybe point out here is that this is homogeneous equilibrium. Okay, homogeneous means you have the same state or phase for all of your reactants and products, right? You'll notice here I had HCl gas, O2 gas, H2O gas, and Cl2 gas. Okay, they're all gases, which makes it homogeneous. If they were all aqueous, it would still be homogeneous. Homogeneous equilibriums are much easier to deal with than heterogeneous equilibriums. Heterogeneous equilibriums have a mixture. So you might have a solid and a liquid turning into a gas and a gas. I do have a couple of videos that talk about heterogeneous equilibriums because there's a few extra steps that you have to worry about there. Okay, once you have your equilibrium expression, if you know the concentrations at equilibrium, it's just the substitute and calculate problem. Now, this is important. This is an equilibrium expression. This is an equilibrium constant. So when you substitute in concentrations, it has to be the equilibrium concentrations. The concentration after everything has kind of balanced itself out. Okay, you can only put equilibrium concentrations into an equilibrium expression. So let's do that. KEQ equals. Now, these are not listed in order, which means that you have to pick out the right number. That is probably the first place where you're potentially going to make a mistake, right? I have listed the concentrations here pretty much in the order you see them in the formula, right? HCl first, O2 next, water next, chlorine last. But when you put them into the formula, right, don't mix them up. So concentration of water is 1.2 moles per liter. So let's put in 1.2. There we go. And it is squared. If you look for the concentration of Cl2 is 2.5. Formula says, please square it. And remember, between these two is a multiplication. In the denominator, you've got concentration of HCl. Well, I have that. Concentration of HCl is 0.25. It says that it should be to the power of 4, so that's power of 4. And then the last thing we have is concentration of O2. Concentration of O2 is 0.35, and it is to the power of 1. Okay, so be very careful that when you're substituting the numbers in, you put the right number in the right place. You don't want to mix them up. Now, if we do our KEQ, there are a couple of places here where your calculator could potentially lie to you. Okay, so if I do 1.2 squared times 2.5 squared and press equals, I get 9. So my numerator is 9. Now, if you attempt to do this entire thing all at once, if you say divide by 0.25 to the power of 4 times, okay, so you did this, divided by this times this, your calculator, my calculator, now believes that this 0.35 is over here. It does not recognize that it's part of the denominator, so I'm going to get the wrong answer. So in order to do this as one step, I am going to have to use brackets, right? So I'm going to have to put brackets around this in my calculator so that way they don't mess themselves up. The other option is you could just calculate out the denominator and write it down, and then do a final step that's a division, right? And perhaps that's what I might do. So 0.25 to the power of 4 times 0.35 to the power of 1, which doesn't do anything. That gives me 1.367 times 10 to the minus 3. And if I do my final division, that'll be 9 divided by 1.367 exponent minus 3. I get a value of 6,584. Now, let's say that you're not totally happy with the scientific notation. Now, if you're going to be doing equilibriums, you're going to have to become confident with scientific notation. But let's say that you want to put it all in your calculator at once. And you're not really happy with the having to bracket everything in the denominator. Well, the way around that, if you have a numerator divided by a denominator and there's a times in it, really you're taking the whole numerator and dividing it by the first piece of the denominator, but then you're also dividing it by the second piece of the denominator. So what I'm going to do is, let's redo the top. 1.2 squared times 2.5 squared. Then I'm going to say divided by, and let's put in the first piece of my denominator, 0.25 to the power of 4. But I'm not just dividing by this, I'm dividing the numerator by this as well. So I'm going to hit divide by again and say 0.35 to the power of 1. And I get the exact same number, 6,584. What it does is it eliminates you having to write down the numerator and denominator separately and then do the division, right? You can throw everything in at once. It also eliminates having to use brackets for your denominator. So it's like total numerator divided by the first part of the denominator divided by the second part of the denominator. It only works when you got a multiplication, which is great because equilibrium expressions always have a multiplication there. All right, so let's say we try a second one. So if we take a look at this, first step is always your equilibrium expression. So KEQ is going to be products over reactants. My first product is a CH4, square brackets to show concentration, power of 1. Now, we didn't write the 1 here. It gets kind of assumed. So I'm not going to write my 1 here because it's also assumed. Because if anything is to the power of 1, it really doesn't change it. I have a second product. The second product is H2O, square brackets to show concentration. Again, it has a 1 in front, so my power is 1, but I don't have to show it. It's just assumed that it's there. Divided by. First reactant is carbon monoxide, square brackets. There is 1, so power of 1, times the second reactant is an H2, square brackets, and because there's a 3, I will cube it. Okay, once you get your equilibrium expression, now it's just substitute and solve. So we got KEQ equals. What is the concentration of CH4? So if we go through our list, CH4 has a concentration of 0.75. 0.75 to the power of 1. Times, what's the concentration of water? We go through our list. Concentration of water is 0.13 to the power of 1. Okay, in our denominator, concentration of carbon monoxide. Carbon monoxide is 0.35. Again, power of 1. And then it's the concentration of H2, and the concentration of H2 is 0.058. This one, though, has a 3, right? You had 3 of them, so it becomes cubed right in your 3. Your first possible mistake in these is that you will put the concentrations in the wrong place. You just mistakenly put them in the wrong spot. The second place where you're going to make a mistake, you'll write your equilibrium expression here perfectly with the cubed. But then you'll be so focused on putting the numbers in that you'll forget to include it here. Okay, so be careful that if you have a power, that you don't forget to include it in the actual calculation. Okay, so if I'm going to do this, I've got 0.75 to the power of 1 times 0.13 to the power of 1 divided by 0.35 to the power of 1. And I'm going to do the double divide thing, right? This is divided by this, but it's also divided by this. So I'm going to hit divide by again, and then I'm going to put in my 0.058 to the power of 3 equals. So that gives me 1,428. Now, the biggest issue here is making your calculator give you the right answer. Because you do have two things in the denominator, it's very easy for your calculator to misunderstand what you want done and to give you an incorrect answer. So my suggestion is to rewind a video a bit, take a look at the problems, attempt to do them yourself, and then compare your answer to my answer. Okay, if you're getting the same answer, then you're on the right track. Now, the other thing that we should probably note here is that equilibrium constants generally don't have units. And the reason for that is that they would all have different units. Right, for this one here, if I talk units, I've got moles per liter for the H2O, which would be squared. I've got moles per liter for the Cl2, which would be squared, over moles per liter to the power of 4 times moles per liter. Now, if you think in your math terms, this is like saying x squared times x squared over x to the 4 times x to the 1, right? If you have two things that have the same base, you can add the powers, right? It's like saying x to the 4. And on the bottom, this to the power of 4, this to the power of 1 is like x to the power of 5. And if you have the same base and you're doing a division, you can subtract. So this would be like x to the power of minus 1. So the units on this would be moles per liter to the minus 1. Let's take a look at the units for the other one. Like if I do this one here, this would be moles per liter for the CH4, moles per liter for the H2O, moles per liter for the carbon monoxide, and moles per liter cubed for the H2. Now again, if we think about it in x's, that's like x to the 1, x to the 1, x to the 1, and x to the 3. If you're multiplying with the same base, you can add the powers. So this would be x squared over x to the 4. If you're dividing, same base, you can subtract the powers. So this would be x to the minus 2. So the unit here really would be moles per liter to the minus 2. Right? For this problem, it was moles per liter to the minus 1. Because this one has different powers, you're going to get a different unit. So while the K values do have units, okay, the units are unique to the equilibrium that it came from, right? So if you have a different chemical reaction, then you'll have different powers and you will get a different unit. So in general, when we do these, we don't give units to the K values. So our equilibrium constants tend to be unitless. Okay, so I do have another set of videos that do talk about the heterogeneous equilibriums. What happens if you have like solid and a liquid and a gas and another liquid. They are a little bit more complex, and if you have to do equilibrium expressions, you're most likely doing both homogeneous and heterogeneous, so I'd suggest you take a look at those as well. So once again, thank you for joining me here at Chemistry with Dr. Clark.